Hey everybody, so my name is Alex Alcantar, and right now I'm going to show you guys a quick and easy way to get down Faraday's law and magnetic flux. Okay, so for those of you guys who don't know, some of these teachers can actually go over and really take a long time to explain it. I want to show you guys a short, easy video just to go over these basic big concepts. So right now with Faraday's law, we know that from my notes, the voltage accumulated around a closed circuit is proportional to the time rate change of the magnetic flux it encloses. You're probably thinking to yourself, what the hell is that, okay? So actually, from Faraday's law, we get Faraday's law from Maxwell's equations. And it pretty much just summarizes the way voltage can be generated by just changing the magnetic field, which is a very simple concept once we break it down. So right now, I'm going to put up Faraday's equation. We have an EMF, which is going to equal to the number of turns times the derivative of a magnetic flux divided by the derivative of time. So you guys can look at that right now. I have EMF, which is my electric motive force, is equal to the number of turns, N, D, which is my derivative symbol. This is going to be a magnetic flux, which I'm going to go over really soon, and this is with respect to time. Okay, so for those of you guys who do not know, magnetic flux, if I just draw a simple magnet really quick with a north end and a south end, we're going to have lines going from the north end to the south end. And those lines are actually our flux density lines, okay? So if you guys can see that little magnet right there that I drew, I have a north and south. We're having lines going from the north end to the south end. If I were to put this in a series motor or a DC motor that has permanent magnets on it, and let's say I put in an accumulator or something that has a little bit of area, okay? So let me just erase this really quick. Let's say I have those lines, those flux lines going through a piece of area. Square, simple area, and we're going to have flux lines coming directly out. I'll make that perpendicular to my area. So if you guys can see, I have my area, which is my block, and I have this line coming straight out, which is B. That could be derived as a vector, and what we're going to do is we're going to have pretty much this coming out as our flux. That little symbol I drew is going to be our flux. Because, you know, sometimes in a perfect world, we're not going to have B always perpendicular to our area. So then what you would do is you would then do the cosine of that theta times your B. Okay? Now we're going to go over the units for magnetic flux. So what do you guys think would be the units of magnetic flux? You guys have any guesses at all? Well, we can derive that from our B cross product of our A. Because it's just a vector, we're going to have a B cross A. We can see that our B is going to be in Teslas, and our A is going to be in meters squared. So if you guys never heard of a Tesla, let's break it down, because you know that can be a little scary to some people. So instead of writing Tesla, I want to write it as a Weber per meters squared. And Weber, it's not the grill, it's actually a unit for our flux density. So we have Webers per meter squared, and I'm going to cross product that times my meter squared. So I have Webers per meter squared times meters squared. I'm going to cancel out both my meters, and that's going to give me my Weber. And that's going to be our unit for our flux. So right now I've explained a little bit of Faraday's law, and I've explained a little bit of the flux density and magnetic flux. I want to give you guys a problem that'll help encapsulate everything for right now. So I'm going to go back to Faraday's law, and I'm going to go back and we're going to do a little problem. This is something I had to do for my Physics 2 class. It's something I really liked, and I think it has everything we have. So let's say I have a piece of round stock, just a piece of metal. So that's going to be a cylindrical tube. And what I'm going to do is I'm going to wrap wire around it. So I'm going to wrap. I have wire wrapped around it. If I do a side view profile, that's a circle coming out of that tube. That circle is going to have some radius. So let's say, I don't know, let's say R is going to be 0.5 meters. You know, just throwing numbers out. We're going to see that our area is going to be pi r squared, which I did the calculations, and it's going to be 0.7853 meters squared. So once we have that area, let's look at what else we got. We have number of turns, which is wrapped around the piece of metal, and I'm going to label that N. It's going to be our number of turns. So let's say, you know, I wrap this around 150 times. After that, we're going to go to our B. Our B is going to be 5 Teslas. So I have my area, my N, my B. So my flux density is going to be my N times my A cross B. When I solve that out, it's going to be 150 times 5 times 0.7853. And you guys can obviously see this, and I explained my units. We're not going to have any units for the number of terms. This is going to be Webers per meters squared just going to cancel out, and you're just going to be left with Webers. So my flux density is going to be in units of Webers. And you guys can just solve this out really quick. I'm running out of time, but I really wanted to just